And if you remember that we have already learned about discrete time Fourier transform. And discrete Fourier transform is where you have the formula x of n exponential minus j omega of n goes minus infinity to infinity is x exponential j omega. Okay, and so this is what we did in uh, our first part of the course, and we learned about the TFT and the properties. The issue with this formula is that here the variable omega is a continuous time variable, and it varies from minus pi to pi. Okay, so it varies from minus pi to pi. So, and we know that using a digital computer, we cannot compute anything which is continuous in nature. So the best we can do is that we can discretize it. Okay? We can only find its value at discrete intervals in time or frequency depending upon the axis. So the continuous Fourier transform is called DTFT, and once you discretize it, that you only compute it at discrete intervals in frequency, it is called discrete Fourier transform. See? So we need to learn about the discrete Fourier transform, especially once in MATLAB. Once in MATLAB, you try to compute uh, Fourier transform, okay? And you say, let's say x is equal to 1 to 100, and you compute plot absolute FFT of x. So actually, it's not computing discrete time Fourier transform. They're showing you this as a discrete or a continuous waveform, but it is actually computing uh, a discrete version of this, and you can see that discrete version. Obviously, instead of plot, if you say stamp, so perhaps stamp. So I'll show you the discrete version of this, and MATLAB, what MATLAB does is कि इसको खुद ही से वो plot करके आपको दिखा देती है. So but actually it is the discrete values that MATLAB computes, and this is very important for us to understand, and that there is no way for the MATLAB or for any computer to work on continuous function except doing them analytically, like finding an expression for it. Otherwise, it can only a computer can only compute these formulas at discrete intervals in time. So this is what the DFT, this chapter is about, computing DTFT at discrete interval in time. Interestingly, this book takes a very different approach, that in order to teach you DFT, it first teaches you discrete Fourier series. Okay, and all of us know about Fourier series. Fourier series can only be computed for periodic function. ठीक है, हमें पता है जो periodic function होते हैं उसकी हम we can compute discrete Fourier series, and we call these discrete Fourier series coefficients. And what these coefficients, they tell us that the contribution of different cosines in a periodic signal. So it was Fourier who first discovered that any periodic signal can be created by adding many cosines, many cosines. And first cosine, the contribution of first cosine will be the fundamental harmonic. This is the fundamental. And we can see by looking at the signal, we can easily plot the contribution of the fundamental cosine. Okay. And also the contribution of DC value. This is C naught coefficient. Then is the contribution of first harmonic, then is the contribution of second harmonic. And as you keep adding the contribution of different harmonics, it start taking the shape of the signal. So your this addition will help, it will start taking the shape of the signal. Okay. start taking the shape of the signal. So many, but the important and interesting aspect is that the contributions are only of the fundamental harmonic, 2 times the harmonic, 3 times the harmonic, 4 times the harmonic, and they only contribute. No other frequency contributes in a periodic signal. This is amazing how Fourier could able to figure this out. And you must be knowing that कि उसका जो पेपर था, it was rejected by the top mathematician Lagrange वगैरह ने उसका पेपर रिजेक्ट कर दिया था. It was only after the death of perhaps Fourier and Lagrange that his paper got published. ठीक है. So because they would not believe that this such a thing could actually be true. If let me show you an animation for you to better understand Fourier series. So this is the contribution of the fundamental harmonic. So fundamental harmonic is the cosine, and then comes a second harmonic, which is always 2f0. So that's why there is another circle whose radius is half of this. So this is the contribution of the second harmonic, and this is the contribution of the third harmonic. And as you see, as you are adding more and more of these cosines, it starts taking the shape of a square pulse. And how many do you have to add? You have to add infinite many cosines for the signal to take the shape of a square pulse. And every harmonic has an amplitude and a phase. Every harmonic has an amplitude and a phase, and these are the amplitudes and the phases that are creating these and converting them in the shape of a signal. So discrete Fourier series is even more interesting because you don't need to add infinite many cosines, as you can only have finite number of these cosines or exponentials. So discrete Fourier series is for periodic signal, that you can break a periodic signal into number of exponentials, exponential j 2 pi k n over n, and every of these exponential has, this is the contribution of every exponential, and these are the exponential. Once you put k is equal to 0, so k goes from 0 to n minus 1. So the discrete Fourier series, it says that you have, if you plot this, it has a cosine and a sine. So first is the DC value. Once k is 0, once k is equal to 1, it is the first harmonic. K is equal to 2 is the second harmonic. Sorry about that. The first harmonic, then the second harmonic, then the third harmonic, then the fourth harmonic. Okay, and the sine and a cosine with different amplitude and phases. Once you add them together, and they are discrete. In this case, they are discrete, and once you add them together, they'll make the shape of the signal. So this is discrete Fourier series, and only this, there is a scaling factor. And remember that 1 over 2 pi, you have to put either with this formula or with the other formula. In one of the formulas, you have to introduce the scaling factor 1 over n. So for any periodic signal, this is how you should visualize this, that there is this periodic signal, and I'm telling you this periodic signal is primarily a summation of n complex exponentials, that once you add them together, you get this periodic signal. Okay, and the good thing about the discrete case is that you don't have to add infinite cosines, only you got to add n cosines or n exponentials to create any periodic signal. So so these x of k's, which are telling you about the contribution of each exponential, they are called discrete Fourier series coefficient, and mostly we call them discrete Fourier series. Okay, a discrete Fourier series. And so Finding DFS, discrete Fourier series, is important. So this is the formula of, and it's also called the analysis formula, which basically tells you the contribution of each harmonic in making up of that signal. The animation that I just showed you, the radius uh, of that circle, the little circles, is basically the contribution of each of the harmonic in making up of that signal. So, uh, uh, these formulas are important. This is the analysis formula, and this is the synthesis formula, which basically is telling that actually a periodic signal is nothing but a summation of n exponentials, where we can find out the contribution of each by using this formula. So this is called discrete Fourier series. And the good thing about discrete Fourier series is that you are not dealing with infinite number of exponentials. These are only finite number of exponentials. So as a matter of fact, using this formula, you can compute the coefficients. And for example, this is a periodic signal. Okay, this is repeating itself from 0 to 9. So capital N is 10. There are 10 samples in it. And capital N is equal to 10 because there are 10 samples in it. So it is repeating after every 10 samples. And we need to find out the contribution of each. Finding the contribution of the DC value is very simple. Why simple? Because if you look at this formula and you want to find out k is equal to 0, so you put k is equal to 0, so exponential of 0 is equal to 1. And it tells us that the contribution of the DC value is, you just add all these samples together, and that will tell you that how much is the DC value. So if you look here and you add all these samples, okay, 1 plus 1 plus 1 plus 1 plus, so there are 5 ones, so you are going to get 5. So that's why you see 5 here. Okay, the contribution of the DC value is the 0th coefficient of the discrete Fourier series, and that can be easily calculated by adding all the samples in the signal. The DC, मसलन अगर ये ऐसे होता कि you have 2 samples here and 2 samples here, so there is no DC value. So you add the sample, you say there is no DC bias in the signal. So computing the DC bias in a periodic signal is simple, and it is also very simple in case of continuous signals, that you only have to integrate them from 0 to t, or whatever is the period, and that tells you the DC bias. Now finding these, the first coefficient, the second coefficient, so to say you put k is equal to 1 in this formula. So here you put k is equal to 1, and that primarily will give you the contribution of the first harmonic, okay, which is the exponential minus j 2 pi k n over n. So the first harmonic is exponential minus j 2 pi k is equal to 1, so n over 10. This is, and how much is the value? This is something which you need to compute. This is the magnitude and the phase. So once you plot this on n axis, it will be a cosine and a sine of some amplitude and phase. So this is the contribution of the first, and what is the contribution of the second harmonic? It is minus j 2 pi 2 n over 10, and the third and the fourth and the fifth and the sixth and the seventh, and so the important is finding. And as you can see from this formula, that it is very simple, that I put the value of k, solve the summation, and I'll give you a Fourier series coefficient. So as you can see here, this is because it's going to be a complex coefficient, so you get a magnitude and a phase, a magnitude and a phase, magnitude and a phase. And you can also get a mathematical expression, like we know that this formula is alpha of n summation n goes from 0 to n, so it is 1 minus alpha raised to the power n plus 1 over 1 minus alpha. So we know this formula. So what this book has done is that it has used this formula, and the formula has given you a closed form expression. Once you put k is equal to 0, You get the 0th coefficient, put k is equal to 1, you get the first coefficient, second. So you are not solving this summation again and again. You have a closed form expression, and you can definitely use the closed form expression to find an expression where by putting a value of k, you get the value of a coefficient. And this expression, for sure, it is guaranteed that is going to be periodic over k is equal to n. So every 10th of this k put 10 and it repeats itself, and we can see that sine is a periodic signal, so every 10th sample is going to repeat itself. So this is Fourier series. Okay, and also remember that we do have no interest in periodic signals, mostly in signal processing, because most of our signals are aperiodic, may it be voice or images or videos or data coming from sensors. So हमारा इंटरेस्ट नहीं है ये पढ़ने में, लेकिन the book has taken this approach for a reason, and we'll shortly find out the reason. Okay, because Fourier series is a mathematical formula, so it obeys many mathematical properties like linearity. That if you have two periodic signal, n has to be the same, and you are scaling and adding them, that obviously the contribution of different cosines will remain as is, only that you scale their respective contributions and add them up together. So it's very easy to perceive this, that if there are contribution of 10 cosines in one and 10 cosines in the other, the same cosines primarily, because the capital N is same. So if you are adding, definitely you're going to have another periodic signal, because this is a periodic signal. So it also would have Fourier series coefficients. So the Fourier series coefficient don't have to recompute. You can just use the previous coefficients for computing that. Similarly, if you shift a periodic signal, you shift a periodic signal, it will remain periodic. Okay, I'll show you an examples in a while. So the Fourier series coefficients are not going to change, because you are shifting the contribution of each cosine will not change. The shift will only introduce a phase, and this is that phase, exponential minus j 2 pi n k m. M is the amount of shift that you have made to the signal. But on the other hand, if you basically are changing the contribution, okay, shifting the coefficients, then it amounts to, because you are shifting the contribution of different cosines, so it is as if you have multiplied that. Basically you have added the frequencies, तो उनकी frequencies के अंदर आपने और उस signal को as if you have multiplied it by an exponential. And we have seen it in discrete time Fourier transform as well, that it is shift in frequency is that you have to add an exponential, because a signal is nothing but a summation of exponentials. So we did a lot of deliberation on this in our discrete time Fourier transform content. Then there is a property which is not there in discrete time Fourier transform. It's called duality property. Why duality? Because once you take discrete Fourier series, the coefficients also make a periodic signal. And if it is a periodic signal, means that again you can take a discrete Fourier series, finding out the contribution of different cosines in this periodic signal. So mathematically it results into a very interesting expression, that a periodic signal has the Fourier series coefficients. These are also periodic, and you again take the discrete Fourier series. So what you find is the coefficients are actually the original signal flipped and scaled by a factor of n. Okay, so there is a mathematical proof for this as well, which we will not cover, but this is important. Duality is important. So, and then there is another important property that says, what if you multiply two discrete Fourier series coefficients together on sample by sample basis, you again get another periodic signal. But interestingly, mathematically, in time, what you're doing is that you are computing a circular convolution because of the periodicity of the signal, circular. So ये भी उसी तरह की property है, where we say multiplication in time is convolution in frequency, and convolution in time is multiplication in frequency. So these are almost the same concept, that multiplication जो है in frequency is convolution in time. So convolution in time अगर आप कर रहे हैं, but it's a circular convolution. It results into multiplication in frequency. So, but how do you do the circular convolution? तो ये थोड़ा सा complex है कि how do we compute the circular convolution of two signals? Let's say हम कह रहे हैं एक है x1 of n, and usually we use this notation to perform circular convolution, x2 of n. So its formula is k goes from 0 to n minus 1. x1, these are periodic signal. So x1, same formula, tilde k, x2 tilde n minus k is the circular convolution, where you get another signal x3 of n, which is also periodic. So periodic convolution requires you to keep one signal as is. तो एक सिग्नल को आपने as is रखना है. Let's say you decided to keep this signal as is, and flipping the other signal, but it's a circular flip. So this is the difference. अगर वो flip होता तो आप इसको ऐसे करके इधर कर देते, ठीक है, इसको ऐसे कर देते, which is done here. So this is a signal, you get a flip, so flip, the whole signal goes on the other side. But the problem is once you are flipping this part here, this part is coming here. वो जो part था वो उल्टा होकर इधर आ रहा है, ठीक है. So a periodic flip is different from a simple flip, because a simple flip would only take your signal on the other side, but a periodic flip will take this on the other side, but the thing which is on the other side will come on this side. So periodic flip में ऐसे आ जाएगा. So you are never short of samples, so to say. You are never have no overlap, partial overlap, full overlap, partial overlap, no overlap. Remember, in convolution we used to have पहले no overlap है, फिर partial overlap है, फिर full overlap है, फिर partial overlap है, फिर no overlap है. But this will not happen here. So तो अब ये इधर नहीं हो रहा, तो what do you do then? So you just, but once you are computing, you are only computing in this window, which is here. Okay. So circular convolution is a bit trickier. कि आपको flip and drag तो करना है. अब once you drag it, interestingly, let's say this will go out of the window, but because this is here, so this will go out and will enter from this side. जो चीज़ निकलेगी वो घूम के वापस आ रही होगी. That's why it is called a circular convolution. Next time, this goes out, but this will come from the other part, which is the other part of the periodic signal which come into the window. So एक circular सा effect है. Anything which is going out is coming back in to the window. And the second thing is usually for the linear convolution, your size of the output is L plus M minus 1. Agar L is the size of x1, M is the size of x2, so the output will have a size of L plus M minus 1. But in this case, both signal got to be have the same period n, and the output should also have the same number of samples as n. So ये एक यहाँ पर थोड़ा सा मसला है. Okay, so there is a problem, but we need to primarily understand that that this is what is going to happen to our signal. Okay, the output. So discrete Fourier series, though we have no interest in learning otherwise, have interesting properties, and these properties are of the periodic signal, and they are like a shift is not a shift, but it is a circular shift. Once you shift a signal, it is a circular shift. For example, if this is a periodic signal and you 0, 1, 2, 3, and if you shift it by 1, so whatever goes out of this will come back from this side. So shift by 1 will be, okay, so जो चीज़ 3 वाला उधर से जाएगा घूम के वापस आ जाएगा. और one another way of easy comprehension is that you even draw the signal in a circle. So this is, let's say, 3, 4, 3, 2, or let's say 4, 3, 2, and 1. So if this is the signal 4, 3, 2, and 1. If you shift it, so you circularly rotate it by 1. So 1 will come on this side. If you shift it by 2, so you basically move it twice. So it will be 2, 1, 4, 3. So it's very easy to find out circular shifts by drawing the signal in a circle. So how about a flip? Otherwise, it's very cumbersome to flip a signal, because I showed you earlier that a flip, this will get flipped, but this will also get flipped. So ये इधर आ जाएगा, इधर आ जाएगा, इधर आ जाएगा. So this is what is going to happen. 4, 1, 2, 3. 0, 1, 2, 3. So this is a circular flip. So a circular flip will make this 4, 1, 2, 3. Another way of doing this is same, that you draw it in a circle. So this is 4, 3, 2, and 1. And now draw it, instead of clockwise, draw it anti-clockwise. Okay, this will plot you a 4, 3, 2, 1. So this is a circular flip. So a circular shift, circular flip can be computed by actually plotting a signal in a circle and just rotating it, or just instead of plotting it clockwise, you plot it anti-clockwise. And now comes the important question, that why to worry about discrete Fourier series? And here is the answer. First, just observe that what this discrete Fourier series is. The formula. This is the formula. Okay, because this exponential minus j2 pi over capital N is used so many times. The book has used this notation, and many publications also uses the same notation, putting instead of exponential, putting w. ठीक है, शायद जिस ज़माने में DSP बन रही थी, तो people would not like to type, इतनी बड़ी-बड़ी चीज़ें बार-बार लिखना, so they use this notation. So book uses this notation, so don't be worried about this. It is actually an exponential of minus j2 pi kn over n. This is a formula for discrete Fourier series coefficients. Okay, so discrete Fourier series coefficients would actually has this formula. अब हम आते हैं discrete time Fourier transform. The formula of which is x of n exponential minus j2 pi, exponential minus j omega. Discrete time Fourier transform. The formula is x of n exponential minus j omega n formula. So there are two issues with this formula. One issue is that omega is continuous. So a computer cannot compute something where the variable is a continuous variable. So you got to discretize it. Currently it varies from 0 to 2 pi or minus pi to pi, because periodic it does not matter. It varies from 0 to 2 pi. So and if you are looking into the Z transform, it is the unit circle which goes from 0 to 2 pi. And if we are looking at a particular plot, then it is 0 to 2 pi or minus pi to pi, because it's going to be periodic. So it's up to you whether you want to consider from minus pi to pi or 0 to 2 pi. So this is the first issue with this formula. Second issue is computer cannot handle a signal which runs from minus infinity to infinity. Okay, obviously it has to be finite signal. So in order to calculate using a computer, asking a computer कि भाई ये मुझे compute कर दो, आपको you got to get away with both of these limitations. Obviously it's a compromise. So पहली चीज आप कहते हैं यार I will only do n samples. Okay, only n samples, not all the samples, because I know my computer has this limitation. I need to give it finite number of samples for it to work on. And secondly, I will divide this omega, this part from 0 to in n equal portions, n equal portions. So I'm sampling the frequency axis on n equal portions. So if total is 2 pi, every portion will be 2 pi over capital N, right? Har ek portion 2 pi capital N 2 pi. So it will start from 0. The first will be, so if I magnify this, 0 say 2 pi, dividing them into n parts. So the first will be 2 pi over n. The second will be 2 into 2 pi over n. The third will be 3 into 2 pi over n, and this nth will be n 2 pi over n, and n se cancel ho gaya to 2 pi aa gaya. Obviously, so you need not, because 2 pi will be same as 0, so you only need to go till this point, which is n minus 1 2 pi over n. Okay, so this basically, if we, so we, instead of having omega, we say it is minus j. Instead of omega, I write 2 pi n k, because k0 will bring me here, k1 will bring me here, k2 will make this sample, k3 will. So instead of omega, you replace omega by this, and obviously you put an n here. So this is the change you make in the formula, that now instead of omega, you have a discrete value on the frequency axis, okay, and regularly sampled. Omega को change कर दिया, and here you have the same x of n. It goes from 0 to n minus 1. Instead of calling it x exponential j omega, so you write it x of k. So this is the formula for discrete Fourier transform. X of n exponential minus j 2 pi k n over n summation n goes from 0 to n minus 1 is equal to x of k. And it has, so it goes in both direction. So mathematically, you can prove that the inverse Fourier transform is the same as is the case in continuous domain. Instead of minus j omega n, it was plus j omega n. And instead of 1 over 2 pi, there are n, so it is 1 over n. So k goes from 0 to n minus 1 x of n. So this is the new pair. Discrete, and this is called discrete Fourier transform. So thoda sa wo hai, discrete time Fourier transform is where omega is continuous. Discrete Fourier transform is where and the omega is discrete, and it has working on a finite signal. So so MATLAB, once you use MATLAB, it uses this formula. Okay, it uses this formula. What is the issue? The issue is, if you look closely, this is the same formula as of discrete Fourier series. सिर्फ उधर tilde डले हुए थे ऐसे, ठीक है? Mathematically, we get the same formula. Why should I care? हैं तो हैं भाई, मुझे क्या फर्क पड़ता है? फर्क किस तरह से पड़ता है? फर्क इस तरह से पड़ता है कि if you even consider that your finite signal as a periodic signal, consider this signal as a periodic signal and compute discrete Fourier series, it will give you the same answer as that of discrete Fourier transform. Okay, so then उससे क्या फर्क पड़ा जी? मुझे आंसर तो मिल गया, मेरे पास सैंपल्स आ गए, मुझे क्या परेशानी है? परेशानी इधर है कि once you compute its inverse, it makes that signal a periodic signal. Mathematically, it's a periodic signal. But again, I should not care, because मुझे तो सिर्फ 0 से n minus 1 samples की care है, वो मुझे मिल गए हैं वापस. Problem ये है कि some of the properties of DTFT are no more valid for these formulas. They are replaced by the properties of the discrete Fourier series. सही है? Issue with discrete Fourier transform. Properties of discrete time Fourier transform are no more valid. For example, shift in time वाली एक हम property पढ़ते थे. If you shift in time, it is exponential minus j omega. अगर d कर दें तो omega d x exponential j omega. A shift in time is multiplication by a phase which is exponential minus j omega d. This is no more valid. For this, once you shift in time, it will be a circular shift. जो चीज़ निकलेगी वो घूम के वापस आ जाएगी. ठीक है? So this property changes. The most important property is convolution in time. जो हम करते थे is multiplication in Fourier. This is no more valid. Now it is the circular convolution. And so once you multiply discrete Fourier series, it will not give you the answer of the linear convolution, rather it will give you answer of a circular convolution. Let's see this in MATLAB. See, let's say हमारा एक signal है x is equal to 1 से 5 कर लेते हैं. So x is a signal 1 2 3 4 5, and h is a signal, it is -1 0 1 2 4 and 2. 1 2 3 4 5 6 सैंपल. So यहाँ पे कर देते हैं. ठीक है जी, ये सिग्नल है x and h, and if you convolve x comma h, you get an answer. And if you try to get the same answer in Fourier domain, so means that first computing the Fourier transform or the discrete or the Fourier transform of x, let's name it capital X, and then compute the Fourier transform of h, let's call this capital H. Okay, then capital Y is capital X dot multiply, so you multiply them on point by point basis, this, and then you take IFFT of Y. So it does not give you the same answer. Where what was the answer of x comma? Okay, answer different हो गया. So this is the second problem with discretizing the discrete time Fourier transform, that property is no more valid. It is giving you circular convolution, length of which is the same as length of the signal 1 2 3 4 5. See, so these are the issues with discrete Fourier transform. Let's quickly learn about this. कि भाई ये जो है x of n exponential minus j omega n is the formula, and it is a function of omega. And omega जो है, it is not discrete. Okay, it is continuous, but it has to be discrete. Or points, the formula cannot work, the computer cannot work from minus infinity to infinity. Only has to be finite. So if you do both of these, it is as if you are dividing this interval into n parts. ठीक है, n points आएंगे. So इसको 2 pi n k में ओमेगा को आप रिप्लेस कर रहे हैं. ओमेगा इज रिप्लेस बाय 2 pi n k. ओके, तो उसका जो फॉर्मूला बनता है वो वही बन जाता है जो डिस्क्रीट फोरियर सीरीज का फॉर्मूला है. ओके, सो यू गेट द सेम फॉर्मूला एज दैट ऑफ डिस्क्रीट फोरियर सीरीज फॉर्मूला. So these are the two formulas. One is the analysis formula, the synthesis formula, and they are exactly the same as of discrete Fourier series formulas. And replacing n, usually book में यहाँ पे भी n लिखा हुआ है. So these are the w of n is exponential minus 3 to power n. तो ये वो दो formulas आ गए हैं. ये मैं आपको पहले दिखा चुका हूँ कि how powerful this FFT, and the concept is that only if you take 2.5% of the DFT of this clown, only center में से इतना सा portion लेके inverse भी करेंगे तो same चीज़ आ जाएगी. तो it has DFT has many properties, and perhaps the most important concept in signal processing, this FFT. Okay, the issue is कि ये periodic है, आपके x का periodic होना तो है ही है, लेकिन n भी periodic बन जाता है. So all the properties are now no more of the properties of the all the properties of discrete Fourier series यहाँ पे आ जाएंगी. ठीक है, linearity वाली आ जाएगी, duality वाली आ जाएगी, शिफ्ट तो सर्कुलर शिफ्ट वाली आ जाएगी जो कि मल्टीप्लिकेशन बाय एन एक्सपोनेंशियल है, एंड द मोस्ट अगेन कम्बरसम इज द कन्वोल्यूशन. सो आपने शिफ्ट करना होगा सिग्नल को, तो यू हैव टू शिफ्ट इट बाय मेकिंग इट पीरियोडिक, देन शिफ्ट एंड देन थ्रो अवे रेस्ट ऑफ द पार्ट. सो जो चीज़ निकलेगी वो वापस घूम के वापस आ जाएगी. So this is an example. If you are shifting it by 1 or 2, so you have to redraw this on both sides, make it periodic, then shift it, and then throw away this part. So ये effect होगा if you are the shift in time is multiplication of your Fourier transform by an exponential. तो a circular shift की property लगेगी. Circular shift की duality हमें पता है कि this is the duality that if x of n का Fourier transform is capital X of k, and you bring it here in time domain and again take its Fourier transform, so it will be n x of minus k. okay, और this is a circular. तो इसको circular दिखाने के लिए वो यहाँ पे एक के इधर एक ब्रैकेट डालता है और इधर n लिख देता है कि this is a circular flip. It is a circular flip. के जिस तरह से आप मसला में अगर आपको ऐसे भी कर हम ये देख लेते हैं सर्कुलर फ्लिप किस तरह से निकालेंगे. ये है, इसको पीरियोडिक बनाएं. अब ये चीज़ तो इधर फ्लिप होकर आ जाएगी और ये चीज़ इधर फ्लिप होकर आ जाएगी. सो बेसिकली दिस हाउ यू कंप्यूट अ सर्कुलर फ्लिप. एंड द इम्पॉर्टेंट इज अगेन द कन्वोल्यूशन इज नो मोर, the multiplication in frequency is no more. This is what we have just seen. It's no more linear convolution. It is circular convolution. Circular convolution. And circular convolution जो है वो compute हो रहा होता है, which we don't want. We don't want ever to compute circular convolution denoted by this. We want this to compute linear convolution. because हमें तो linear convolution का आंसर चाहिए. But how do you compute circular convolution? ये सिग्नल है, ये है. If you decided to flip this one, तो इसको periodic बनाएंगे पहले आप. So this is periodic. और फिर इसको flip करेंगे. Okay? So ये part इधर आ जाएगा और ये part इधर आ जाएगा. इसका flip उधर आ जाएगा, इसका flip उधर आ जाएगा. And once you have this flip, then you start shifting, flip and drag. So you are dragging, but what the drag is doing, whatever sample gets out will come in from the other side. Whatever sample get out will come in from the other side. Whatever sample get out will come in from the other side. और आप वही multiplication addition उसी तरह से करते रहेंगे. So this is the circular convolution. ठीक है, ये कि जो सैंपल बाहर यहाँ से निकलेगा वो सैंपल यहाँ पे आ जाएगा, जो सैंपल यहाँ से निकलेगा वो सैंपल यहाँ पे आ जाएगा. तो ये सर्कुलर, ये भी इस तरह से एग्जाम्पल है कि सर्कुलर कन्वोल्यूशन. हाउ डू यू कंप्यूट सर्कुलर कन्वोल्यूशन? बट द कन्वीनियंट इज दैट यू अगेन ड्रॉ इट ऑन अ सर्कल. एक को क्लॉकवाइज ड्रॉ करेंगे, एक को एंटी क्लॉकवाइज उसको फ्लिप करना है, और सर्कुलर कन्वोल्यूशन हम इस तरह करके निकालते रहेंगे. मैं एक आपको एग्जांपल करके देता हूँ. द सेम एग्जांपल लेट्स से दैट आई डिड इन मैटलैब. ठीक है, मैं थोड़ा सा ये करके दिखाता हूँ आपको. सो हियर द टू सिग्नल्स आर, लेट्स से कि x हमारा ये था, h हमारा ये था. ठीक है, 1 2 3 4 5 -1 0 1 2 4. सो आप सर्कल ड्रॉ करेंगे ऐसे 1 2 3 4 5. ओके, एक पे लिखेंगे 1 2 3 4 5. इसको आप दिस इज माई 0. ओके, and now use another color. If I can use let me use the same pen. For some reason मैं स्क्रीन शेयरिंग में वो मुझे ऑप्शन दे रहा. और I can, अच्छा चलिए अभी हम ऐसे कर लेते हैं. And the other signal, instead of writing it clockwise, you write it anti-clockwise. Okay. Other signal क्या था जी? -1 0 1 2 4. -1 0 1 2 4 was the other signal. -1 0 -1 0 1 2 4. So you write the other signal counterclockwise. Then do point by point multiplications and add the sample that we do in convolution. So -1 हो गया, 4 2s the 8 हो गया, 3 2s the 6 हो गया, 4 1s the 4 हो गया, 5 0s the 0 हो गया. तो ये आ गया. इनको ऐड कर लें वापस में. 8 6 4 10 18 -1 70. ये 17 आंसर आ गया. ओके. So what you have done is flip and drag. एक को ऐसे लिखा. So multiply them together, 17. Let's see what is the answer of our first sample. Circular convolution 70. You see this 70? तो हमारा पहला वैल्यू आई 70. लीनियर की क्या आनी थी? -1. Because not a linear convolution, so it is giving me a 17, which perhaps is of no use to me, but still. अब इसको एक दफ़ा आप so flip and drag. So move. Now, once you move this, this 4 will come here, this 2 will come here, this 1 will come here, this 0 will come here, or here will be -1. Now again you do the multiplication. 0 1 is the 0, 2 minus 2, 4 3 is the 12, 4 2 is the 8, 5 1 is the 1. So अब इसको आप ऐड कर लें. ठीक है, 12 20 हो गया, 25 और 2 23. So let's see what are we getting here. 23. ठीक है, ये 23 आ गया. So we get the next again. You keep on doing this, and Dr. Ali will perhaps, inshallah, will give you more examples to do the exercise. ये करते रहेंगे और आपका and interestingly, the only value you get is same as the last value, 6 and 6. Rest all the values are different. Okay, so let me just write down this answer: 17, 23, 24, 26. 17, 24, किसी ने याद रखना है इसे. 23, 24, 26. 17, 23, 24, 20 and 6 ये था, है ना. 17, 23, 24, 20 and 6. 17, 23, 24, 20 and 6. और उसको भी याद रखो, -1, -2, 0, 6, 18, 25, 26, 20. याद है किसी को? -1, -2, -2, 0, 6, 18, 25, 26, 20. 6, 18, 25, 26, 20. So I want you to get this answer, which is answer of linear convolution. I am getting this answer, which is answer of circular convolution. Okay, so they are different, only this value is same. And you know how to compute linear convolution. I need not to tell you this. तो flip and drag करते जाएंगे, आंसर आता जाएगा. No overlap, तो फिर partial overlap, then full overlap, then partial overlap, then overlap. But interestingly, अगर आप देखें, because there has to be a relationship, and relationship is very simple. कि जितना है circular convolution उतने को cut कर दें linear convolution को, and bring all the values which otherwise you are going to throw away. Means you are cutting it down, but bring them and write them here. 18, 25, 26, 20, और इसमें add कर दें. So this is the effect of the samples coming back into the picture, that they are actually corrupting your linear convolution in a very systematic manner. तो ये सारे के सारे इसमें आगे add हो जाएंगे. So 18 minus 1, 17, 25 minus 2 is 23, 26 minus 2 is 24, 20 and 6, which is the answer of the circular convolution. Okay, see, so means the linear convolution you can compute by actually computing circular convolution. You can compute by actually computing linear convolution and bringing जितने भी पॉइंट का वो सर्कुलर कन्वोल्यूशन है ना, बाकी सैंपल्स को इधर से इधर लेकर आ जाएंगे। अच्छा, ये इंटरेस्टिंग है बहुत ज़्यादा कि अगर लेट से मैं कहूँ नहीं यार ये 5 पॉइंट नहीं 6 पॉइंट कर दो इन्हें, यानी कि ऐड 0 0 इन बोथ दी सिग्नल्स and then repeat this. So in MATLAB, if I'm doing it in MATLAB, I say भाई ऐसा करें कि ये जो आपने, मैं इसको एक ही दफ़ा लिख देता हूँ, IFFT of FFT of FF of X dot multiply FFT of H, ठीक है, सॉरी, ये आया था अभी हमारा कन्वोल्यूशन। मैं कहता हूँ नहीं, आप ऐसा करें कि x जो है ना, जो भी x था उसमें एक 0 और डाल दें, और जो भी h था ना, so whatever h you had, put another 0 in it. So you make length of the signal from 5 to 6 by putting zeros, and now you use the same formula, sorry, ये वाला फॉर्मूला। अब देखिए क्या हुआ कि आपका 1 2 3 4 5 6 पॉइंट्स आ गए, 6 पॉइंट्स आ गए, ओके, 6 पॉइंट्स आए, और जो हमारा कन्वोल्यूशन था x, h, उसके अब 2 पॉइंट सेम है, 6 and 18, 6 and 18, ओके, दिस इज इंटरेस्टिंग कि 2 पॉइंट सेम है, बाकी सारे डिफरेंट हैं, ओके। नाउ इफ यू keep adding more and more zeros, it means that I getting more and more correct points. And how many zeros should I add? Exactly the length of the output. If I add, let's say कि x में मैं करता हूँ 5 थे ना सैंपल, तो 2 3 4, if I add 4 zeros to make the length of x h 7 and also the length of x is, अच्छा ये मेरा ख्याल 1 2 3 4 5, एक ज़्यादा ज़ीरो हो गया, चलो कोई बात नहीं, and length of x as, so length of h and length of x as x, में एक ज़ीरो मैंने ज़्यादा कर दिया, लेकिन कोई बात नहीं, 1 2 3 4, तो पहले एक ज़ीरो डाला हुआ था ना। and now if I use this IFFT and do the convolution, I get the exact answer, 1 minus 2 minus 2 0 6 18 25 26 20 0. अच्छा, so the trick is while you are computing circular convolution, like you are using FFT to compute the linear convolution, all you have to do is append requisite number of zeros. यहाँ पे जो था सिग्नल, एक सिग्नल था 1 2 3 4 5 और 0 0 0 0. The other signal was -1 -1 0 1 2 -2 4, -1 0 1 2 and 4, ये दूसरा सिग्नल था, इसमें भी 0 0. And now perform the circular convolution. 1 2 3 4 5 6 7 8 and 9, इतने सैंपल बने। तो ये है आपका 1, एक को अंदर लिखें सर्कल के, 1 2 3 4 5 6, और सॉरी 0 0 0 0, और दूसरे को उल्टा करके लिखें, -1 0 1 2 4 0 0 0 and 0. अच्छा, ये क्या कर रहा है कि by appending the 0 it is making sure that जो करप्ट कर रही थी चीज़ें वो they are always multiplied by 0. So these 4 samples are multiplied by zeros, and these 4 samples are also multiplied by 0. So first sample is -1, which is the answer of the linear convolution. So you have tricked the circular convolution to give you answer to linear convolution. by appending a number of zeros so that even you flip, but the flip part that is coming in and corrupting your answer are all zeros. तो ये बड़ा interesting सा trick है, और this really comes to our rescue, that now actually I can use the property that convolution of x into h even by performing discrete Fourier transform is multiplication provided length of x and length of h should be L plus m minus 1. अगर इसकी length L है, इसकी m है, तो इसमें आप डालेंगे you will add m minus 1 zeros, और इसमें आप डालेंगे L minus 1 zeros to make the length of the signal same, and that will be your n. And after appending these number of zeros, फिर आंखें बंद करके आप इसका DFT लें, आपको आंसर सही मिलेगा जो कि फोरियर ट्रांसफॉर्म का आंसर है. सो MATLAB के लिए if you're doing this in MATLAB, क्लियर स्क्रीन क्या होता है यार MATLAB में, ये आ गया. ओके, सो माय x इज दिस, माय h इज दिस. लेट मी, मैं इसको x को दोबारा लिख के आपको दिखा देता हूँ. x था हमारा 1 से लेके 5 तक नंबर्स, और h था हमारा -1 0 1 2 and 4. okay जी. तो अब अगर if I want to use FFT, which we use to actually implement a system, means to actually perform convolution, ठीक है. So there are two ways to perform convolution. One is use the convolution summation, वो सारा कुछ करें आप, flip, drag, जो किस, और वो structures जो हमने सीखे, DFS1, DFS2, डायरेक्ट फॉर्म 1, डायरेक्ट फॉर्म 2, वो उस तरीके से आप करें कन्वोल्यूशन, स्पेशली फॉर FIR सिस्टम्स. एंड सेकंड इज कि यूज FFT, टेक FFT ऑफ x, टेक FFT ऑफ h. ओके, लेकिन कितने पॉइंट का? L plus m minus 1 पॉइंट्स का. तो आप करेंगे IFFT, FFT ऑफ x, हाउ मेनी पॉइंट्स? नाउ 9 पॉइंट्स. इस तरह MATLAB में आप लिख सकते हैं कि 9 पॉइंट्स करें. FFT of H, how many points? 9 points, because 9 points is the length of the output signal. So जितनी आउटपुट सिग्नल की लेंथ है उतने पॉइंट का FFT लेना जरूरी है. उससे ज़्यादा का भी ले सकते हैं, ठीक है, उसको कोई मसला नहीं होगा, एटलीस्ट उतना. और पीछे आपके दिमाग में बताऊँ क्या चल रहा है, अच्छा वो इतने जीरोज आ गए, कैसे लिखा. लेकिन magically now it is actually performing linear convolution to say you get the correct answer. Okay, this is the correct answer. What if you take more? भाई ज़रूर लें, हमारी तरफ से आप 20 ले लें, ठीक है, कि 20 पॉइंट्स का ले लें आप FFTs, तो वो ऑटोमेटिकली बाकी सारे जीरोस होंगे, आपका आंसर जो होगा वो 9 पॉइंट्स का वैलिड आंसर आएगा आपके पास. सो दिस इज़ इम्पॉर्टेंट. ओके, दिस इज़ वेरी वेरी इम्पॉर्टेंट कि the property is very very important कि जो circular convolution वाली property है. And I have told you how to calculate circular convolution by drawing one signal clockwise and spreading the other signal counterclockwise, doing the point by point multiplications, adding the samples, getting the answer. But our interest is not in circular convolution. I have zero interest in circular convolution. I want my FFT to give me answer to my linear convolution, and I have learned a very easy trick. Appending enough number of zeros, this will give you answer to linear convolution as if you have performed linear convolution. सही, तो ये important चीज़ थी. अच्छा, अब दूसरा एस्पेक्ट आता है कि अच्छा यार ये तो बड़ा अच्छी बात है कि मैं x का भी FFT ले लूँ, ठीक है. मतलब मैं कहता हूँ मैं क्यों मुसीबत में पड़ूँ, मैं x का FFT लूँ, ऑब्वियसली n पॉइंट, और मैं h का भी FFT ले लूँ, ऑब्वियसली n पॉइंट, ठीक है. दिस इज n पॉइंट where n is length L plus m minus 1. Then I multiply them together, x h of k, point by point multiplication. and then I take IFFT inverse Fourier transform ले लूँ IDFT तो मेरा YOFN आ जाएगा. So it's a very good technique. Okay, but what is the problem in this technique? The problem is that you require for x of k, n goes from 0 say n minus 1, x of n exponential minus j 2 pi k n over n. ठीक है? So it requires n complex multiplication and n minus 1 complex additions for computing FFT of x. Then computing FFT of h will require n complex multiplication and minus 1 complex additions. ये multiplication है, ये additions है, और फिर इनको multiply करना है आपस में. That further requires n complex multiplication. और फिर इसका IFFT लेना है. Then again requires inverse discrete Fourier transform लेना है आपने x dot h का. Then that further requires n complex multiplication and n minus 1 addition. So in total requires n 4n complex multiplications and 3 into n minus 1 complex addition. Very computationally intensive. So obviously मुझे वो जो convolution है वो तो सिर्फ l plus m minus 1 जो n है once you are dragging and flipping and dragging, तो वो मुझे इतनी ज़्यादा complex multiplications की ज़रूरत नहीं पड़ती है उसमें जितनी कि यहाँ पे पड़ रही है. Okay, so that's an issue that it is not computationally effective to perform to use this technique. अच्छा, अब देखिए ये जो मसला है कि FFT की computational complexity बहुत ज़्यादा है. Okay, so FFT has computational complexity and you know how to do this because आप doing complex multiplication कर रहे हैं, addition कर रहे हैं इस loop के अंदर और हर value के लिए कर रहे हैं तो n square हो जाएगा sorry because ये तो एक value के लिए है ना n complex multiplication and n minus 1 addition and then you are doing it for n values so n square complex multiplications आ जाएंगे इसमें. Okay, so अब देखें किसी ने ये पूली 2 की दो साइंटिस्ट थे like amazing guys, इन्होंने एक using a very simple trick they showed in 1967 कि an 8k point DFT though otherwise would take 30 minutes to compute DFT. ठीक है, DFT compute करने के 30 मिनट आप जाके खाना शाना खाने चले जाते थे लोग यूनिवर्सिटी से अच्छा से DFT and go eat your lunch and come back and it will be still computing अगर fast food से खा रहे हैं आप. So they showed that they could do it only in 5 seconds. So just imagine the revolution they brought to digital signal processing. Otherwise it was all in theory signal processing. Also FFTs are used, Fourier transforms are used in radars. और radar में मैं अक्सर एग्जांपल देता हूँ जहाज आया तो 30 मिनट बाद आपको पता लगना है कि there is an aircraft in the sky and so that information is useless. But 5 seconds is okay. So they showed even in 1967 that they could actually compute DFT which otherwise would take 30 minutes in 5 seconds. Okay. So अब देखें convolution otherwise would require m into n number of multiplications. ठीक है, for to n point convolution. m point आपके यूनिट्स हैं तो m मल्टीप्लिकेशन होंगी एक में और n इंटू m टोटल मल्टीप्लिकेशन हो जाएंगी. लेकिन अगर आप FFT में आते हैं तो आपकी n स्क्वायर मल्टीप्लिकेशन एक दफ़ा होंगी फिर एक n स्क्वायर होंगी फिर एक n स्क्वायर होंगी और इफ लेंथ लाइक n प्लस m माइनस 1 इसने l प्लस m माइनस 1 लिखते थे ज़्यादा अच्छा था तो आपकी इतनी ज़्यादा मल्टीप्लिकेशन एंड एडिशन चाहिए हैं आपको to use this formula. So nobody would actually use this formula if Cooley Tukey would not have invented the fast way of computing Fourier transform. तो अब ये this is the last topic. सही है. कि लेट्स सी कि उन्होंने क्या जादू किया. The Kuli Tuki, what magic did they play? जैसे exponential minus j 2 pi k n n n is equal to 0 से n minus 1 x of k, and let us write w of n k n instead of writing all this. Okay, उन्होंने कहा कि let's split this, divide and conquer. Split this summation in two parts. One is for even indices, the other is one for odd indices. This is the only trick. ठीक है, इनका इसको हम करेंगे even indices 0 2 4 till n minus 1, और फिर एक समेशन और करेंगे हम 1 3 5 7 till n minus 1. Okay, those summations, yes, there is absolutely no problem. We have the same formula. Sorry about, इसका मैं w लिख देता हूँ, n k over n summation x of n w of n n k. तो ये उसने कहा जी इस तरह से तोड़ देते हैं हम even, and then we add them together, so we get the same answer. Obviously we are going to get the same answer. So this is the simplest trick he played. Then he said, instead of writing the ugly way of writing even and odd indices, so he found a smarter way of writing even and odd indices. That was, okay, r goes from 0 say n by 2 minus 1 x of r w of the 2r and w of 2 n k की जगह r n k. मैं भी एक्सप्लेन करता हूँ इसको. प्लस r goes from 0 से n over 2 minus 1 2r plus 1 w of 2r plus 1 into k. ठीक है, for example you put r is equal to 0, so you get x of 0. You put r is equal to 1, you get x of 2. You get r is equal to 2, you get x of 4. So just a smarter way of writing inner and odd indices. Similarly यहाँ पे x0 डालेंगे तो x1 आ जाएगा, 0 डालेंगे 1 डालेंगे तो 2 आ जाएगा, 2 डालेंगे तो सॉरी 3 आ जाएगा, 2 डालेंगे तो 5 आ जाएगा. सो एक इंडेक्स इधर, एक इधर, एक इधर, एक इधर, 2 0 1 2 3 4 5 स्प्लिट कर दें और इस फॉर्मूले में डाल दें. But the trick he played, that you remember this exponential minus j and this, इसने इस 2 को यहाँ से उठा के इधर लिख दिया, ओके, n by 2. एंड सिमिलरली उसने इसको ओपन किया और इस 2 को उठा के नीचे लिख दिया इधर n में. So the trick he played was a w n 2rk और w k n, इसको ब्रेक कर दिया ऐसे करके और इस 2 को इधर लिख दिया. So the formula he wrote was x of k r is equal to 0 n by 2 minus 1. आवाज़ वो कंपनी थी जो हमने बनाई थी अबाउट 20 years back, आवाज़, एंड हमने इस पर वॉइस ओवर IP के सोल्यूशन पे काम कर रहे थे और हमने कोई $17 million रेज किया था इसके लिए. सो ये स्लाइड पे कब से चल रहा है. सो दिस इज x of 2r w rk n by 2 plus w n k summation r is equal to 0 से n by 2 minus r, मैं इधर लिख रहा हूँ x of 2r plus 1 w of n by 2 rk. So this is the formula. If let's say I have these 8 points FFT 0, 1, 2 से लेकर x7 तक, the simple thing what he did was उसने कहा x0, x2, x4, x6 इसको दे दें और x1, x3, x5 और x7 इसको दे दें. लेट्स से अगर सिग्नल मेरा होता 0, 1, 2, 3, 4, 5, 6, 7, तो पहला सैंपल इसको दे देते, दूसरा वाला सैंपल इधर, तीसरा सैंपल इधर, चौथा सैंपल इधर. इस तरह करके हम स्प्लिट कर देते सैंपल्स को. लेट्स से इफ आई हैव, मैं कुछ वैल्यूज डाल के दिखा देता हूँ आपको. 3, 5, 4, -2, 2, 3, 7, 0, 1, 2, 3, 4, 5, 6, -3. So you split even indices on this side. 3, 4 should make 2 signals. 3, 4, 2 and 7 इस साइड पे, और ऑड इंडिसेस वाले जो सैंपल हैं 5, -2, 3 and -3 on this side. ठीक है, इसको दो सिग्नल्स में स्प्लिट कर देते. 3, 4, 2 and 7 इधर, 3, 4, 2 and 7 इधर, and 5 and -2 and 3 and -3 here. You split this signal into 2 signals. And the trick is now you compute 2 4-point DFTs. ये जो है 2 4-point DFTs. तो इन दोनों का 4 पॉइंट का DFT निकाल लें. 4-point DFT. Obviously पहले आपको 8 के लिए 8 स्क्वायर मल्टीप्लिकेशन चाहिए थी, विच इज 64. इसके लिए आपको 4 स्क्वायर चाहिए, 4 4s तक, तो टोटल 32 चाहिए, उधर आपको 64 चाहिए थी. So you have saved like in number of multiplication, and then obviously there are few more multiplications that you have to merge them together, add them together while you multiply this part with W and K. So अगर मैं इसको ड्रॉ करना चाहूँ तो बहुत आसान सा है कि आपने 8 पॉइंट DFT की जगह 2 4 पॉइंट के DFT निकालने हैं. 4 पॉइंट DFT using the same formula. But these 4 points are x0, x2, x4, x6. These 4 points are x1, x3, x5, x7. तो इसके 4 आंसर आएंगे जाहिर है, और इसके भी 4 आंसर. Then merge these answers together. Merge these answers together by using this relationship, which is कि W and K से मल्टीप्लाई करते करते ऐड करते जाएं. सो K0 के लिए आप इस वाले को, इसको 4 को आपने इस तरह से ऐड करना. सी तो लेकर आए यहाँ पे इस आंसर को, इन दोनों को ऐड कर दें. बट उससे पहले इस आंसर को W0 8 से मल्टीप्लाई कर दें. अब इस वाले आंसर को इधर लेकर आए और इसको W8 1 से मल्टीप्लाई करते हैं. इस वाले आंसर को इधर लेकर आए, इसको W8 2 से मल्टीप्लाई करते हैं. अब इस वाले आंसर को, फोर्थ वाले आंसर को इधर लेकर आए और इसको W8 3 से मल्टीप्लाई कर दें. और फिर इधर वाले आंसर को, ऊपर वाले आंसर को, दिस वॉज द ट्रिक बेसिकली. मैं भी थोड़ा सा आपको एक्सप्लेन करता हूँ कि जब ये आ गया कि y ऑफ k जो है, सॉरी x ऑफ k जो है, लेट्स से इस पार्ट को हम कह लेते हैं g ऑफ k और इस वाले पार्ट को कह लेते हैं h ऑफ k. सो इज g ऑफ k प्लस W8 k h ऑफ k. सो सेविंग कहाँ पे हुई? सेविंग यहाँ पे हुई जब आपने x0 निकाला तो वो तो सिंपल आ गया G0 प्लस W80H0. इसका एक सैंपल इसके एक सैंपल में ऐड हो गया. इसी तरह x1 जब निकाला तो इधर 1 आया, इधर 1 आया, इधर 1 आया, इधर 1 आया। जब आपने 2 निकाला, ये वाला 2 वाला आंसर, तो इधर 2 आ गया, इधर 2 आ गया, इधर 2 आ गया, इधर 2 आ गया। सो interesting is once you compute x of 4, x of 4 is g of 4 plus w8 of 4 h of 4. But interestingly, because it is a 4-point DFT and it is periodic over 4, so h g of 4 वही होगा जो g of 0 है, h of 4 वही होगा जो h of 0 है. So here is the saving, that you are no more computing all these points, you are reusing the answer. और उसने सिर्फ इस divide and conquer में इसको effectively use किया कि you can reuse half of the points. So means के अब इधर आपने इसी को use करना और इधर सिर्फ एक मल्टीप्लिकेशन आएगी जो 4 और 8 से है। सिमिलरली इस वैल्यू को निकालने के लिए आपने इसकी सेकंड वैल्यू को यूज़ करना है, इस वैल्यू को निकालने के लिए इसकी थर्ड वैल्यू को यूज़ करना है, इसको फोर्थ को, और साथ एक फैक्टर से मल्टीप्लाई करते जाना है विच इज़ कॉल्ड अ ट्विडर फैक्टर, W। अगर मैं इसको नीट सा आपको ड्रॉ हुआ हुआ दिखाऊं तो आपकी, सो दिस इज व्हाट ही डिड, ठीक है। इसको इवन इंडिसेस और ऑड इंडिसेस में डिवाइड कर दिया, उसको स्मार्टली ऐसे लिख लिया, r गोज फ्रॉम 0 n by 2 minus 1 w of 2r k n minus 1 2r plus 1 2r plus 1 k। ओके, इसको स्मार्टली ऐसे लिख लिया और ये मैंने भी आपको करके दिखाया कि 0 2 4 6 1 3 5 7 सैम्पल्स हैं। अगर ये हैं तो जो इंडिसेस हैं हाफ यू गिव to this and odd indices you give to this and then compute 2 4 point DFTs इस तरह करके, और उनको फिर इस तरह करके मर्ज करा दें आपस में। और सेविंग कहाँ है, 0 पे नहीं है, 1 पे नहीं है, लेकिन जब 4 पे आएंगे तो फिर 0 यूज हो जाएगा। once you come to 5 again use this, once you come to 7 you again use this is where the saving is. So because you can always write, इसको आप n by 2 लिख सकते हैं, ठीक है, बिकॉज ये 2 को यहाँ से उतारें और इस तरह कर दें एक्सपोनेंशियल से, तो यू कैन राइट, सो यू कैन राइट दिस एज एन n by 2 point DFT and this also an n by 2 point DFT with this factor which gets multiplied, it's called Twiddle factor. So you have already saved, जैसा मैंने आपको करके दिखाया, instead of 64 you have only 40 multiplications and you have already saved this। और ये वो है कि x0 x2 x4 x6 यहाँ पे 1 3 5 7 यहाँ पे G0 G1 G2 G3 H0 H1 H2 H3। सो x0 निकालने के लिए you use this और इसको जाते हुए इससे मल्टीप्लाई, x1 निकालने के लिए G1 H1, x2 निकालने के लिए G2 H2 x3, and now here are the savings that you again use G0 and H0 with this Twiddle factor multiplication, Twiddle factor multiplication. Now obviously a question must come to your mind, why even I am computing a 4-point DFT, why not to divide it into 2 parts, कि पहला सैंपल इसे दे दूं, दूसरा इसको दे दूं, तीसरा इसको दे दूं, चौथा इसको दे दूं, और अब 2 point DFT बनाऊं और फिर उनको मर्ज कर लूं to get a 4-point DFT। सिमिलरली इधर भी ये करूं 1 3 5 7 और 2 point DFT बनाऊं और उनको मर्ज कर लूं। सो दिस इज अ ट्रिक विच इज यूज्ड कि आप तोड़ते जाते हैं इसे। सो यू हैव, जब तक 2 पॉइंट नहीं रह जाते, 0 4 2 6 1 5 3 7 2 पॉइंट DFT किया, 2 पॉइंट DFT किया, 2 पॉइंट DFT किया, और यहाँ से ये दोगे 0 4 2 पॉइंट है एंड देन इट इज 1 4 देन इट इज 2 4 देन इट इज 3 4, बट टू रीयूज दीज हम इसको W0 8 लिखेंगे और इसको W2 8 लिखेंगे। सो वी टेक दिस 2 up so that we can use the same Twiddle factor in our computation। हमें दोबारा इसको इस एक्सपोनेंशियल को कंप्यूट ना करना पड़े। बट 2 points 2 points 2 points 2 points makes 4 points, 4 points 4 points, the 4 points makes 8 and 8 points। so ट्रिक बहुत सिंपल सा है कि आपके पास लेट्स से 16 पॉइंट का DFT है, you break it down to 8 point DFTs। Now don't compute 8 points, break it down into 4 point DFTs, don't compute even 4 point DFTs, break it down into 2 point 2 point 2 point 2 point 2 point 2, merge them together, merge these two DFT together to 4, then merge to 4 to get 8, merge to 8 to get 16. So if it is power of 2, so FFT works on power of 2. और ये हमने देख लिया, if your signal is not power of 2, add enough zeros to make it power of 2. Or MATLAB will do it by itself, so you need not to worry. Once you say, I'll just add the zeros by itself, but preferably if it is not power of 2, MATLAB adds these many zeros and compute the and keep splitting. अब इंटरेस्टिंग है कि 2 पॉइंट DFT क्या होता है. देखें 2 पॉइंट DFT है 0 से 1, x of n w n k2 which is एक्सपोनेंशियल माइनस j2 by nk over 2 0 से 1. इसको ओपन कर लें समेशन को, ये तो आ जाएगा. फॉर फर्स्ट वैल्यू यू ऐड सिग्नल, फॉर सेकंड वैल्यू सब्ट्रैक्ट सिग्नल. सो सिंपल. सो कंप्यूटिंग 2 पॉइंट DFT इज सिंपल. एक दफ़ा ऐड कर दें और एक दफ़ा सब्ट्रैक्ट कर दें, फिर 2 पॉइंट का सिग्नल आ जाता है. इसका क्या मतलब हुआ? अब देखिए, लेट्स से मैं आपसे कहता हूँ कि जी आप ना एक सिग्नल है, लेट मी हैव द सिग्नल हियर, 0 1 2 3 4 5 6 7 तक कर लेते हैं, 2 कर लेते हैं, ये 5 कर लेते हैं, 3 कर लेते हैं, -1 कर लेते हैं, -4 कर लेते हैं, 2 3 4. लेट्स से दिस इज अ सिग्नल, ठीक है, व्हिच इज 2 5 3 -1 -4 2 3 4 1 2 3 4 5 6 7 8 पॉइंट्स हैं, ठीक है. तो अब हमने क्या करना है, इनको स्प्लिट करना है. पहले 2 5 3 -1, तो इसको स्प्लिट करना है. इट इज 2 5 3 -1 -4 -5 sorry -4 and 2. Do something with the sharing. Let me just reshare it for the okay. So इधर मैं दोबारा से करता हूँ इसे. 2 5 3 -1 -4 2 3 and 4. ये आ गए दो हिस्सों ऐसे करके, ठीक है. अब इसको फर्दर आप स्प्लिट करेंगे. 2 3 -4 and 3. ये आ गया. ओके, सो यू स्प्लिट. सो अब इन 2 पॉइंट्स का FFT निकालेंगे. How you compute FFT of these 2 points? By adding them together. 2 - 4 is -2 and subtracting them. 2 minus is 6. So adding them 3 + 3 is 6 and subtracting 3 - 3 0. So ये दो पॉइंट्स के आ गए. जब ये आ गए तो इनको then you merge them together. इसको मर्ज करेंगे, वही टोटल फैक्टर से मल्टीप्लाई करके इनको मर्ज करेंगे, 4 पॉइंट आ जाएगा. सो कंप्यूटिंग इज दैट यू एंड अप ओनली कंप्यूटिंग 2 पॉइंट्स. और हाउ डू यू कंप्यूट 2 पॉइंट्स? बाय जस्ट एडिंग. इन दोनों को ऐड कर लेंगे और इधर सब्ट्रैक्ट कर लेंगे, तो ये आ जाएंगे पॉइंट्स. इसी तरह से जो भी होगा, इनको ऐड कर लेंगे और इनको सब्ट्रैक्ट कर लेंगे, इनको ऐड करेंगे, इनको सब्ट्रैक्ट करेंगे, इनको ऐड करेंगे, इनको सब्ट्रैक्ट. So you add and you subtract, and you add and you subtract. This is all you do, and then you merge, and then you merge again, then you merge again. So you merge like this. So this is the discrete फोरियर ट्रांसफॉर्म। ओके, डिस्क्रीट फोरियर ट्रांसफॉर्म इस तरह से होता है। अब सिर्फ एक चीज़ रह गई, if you're writing a computer program, how do you generate these indices 0, 4, 2, 6, 1, 5, 3, 7? ये बड़े यूनिक से इंडिसेस हैं और ये बड़े इंटरेस्टिंग सा किसी ने सोचा होगा, और नाउ इट इज़ पार्ट ऑफ एवरी डिजिटल सिग्नल प्रोसेसर, कि अगर आप जो इंडिसेस इस तरह जनरेट होने हैं, 0 होना है, फिर 4 होना है, फिर 2 होना है, फिर 6 होना है, ठीक है, फिर 1 होना है, फिर 5 होना है, फिर 3 होना है, फिर 7 होना है। ओके, तो उसने कहा अगर आपके पास ये है, and what you do is that you add instead of adding 1 from here, you add 1 here, और कैरी को इधर चलाने की बजाय इधर रिवर्स प्रोपेगेट करा दो, तो you generate these indices. Okay, so you generate these indices. So this is called bit reverse addressing. For example, इसमें जब ऐड करेंगे तो आ जाएगा 0, 0 and 1 which is 4, which is this index. इसमें दोबारा से 1 ऐड करेंगे तो 1 + 1 0, 1 कैरी, 1 0 2 आ गया which is this index. इसमें फिर 1 ऐड करेंगे तो 1 1 0 which is 6 this index. फिर 1 ऐड करेंगे तो 1 1 0 1 1 0 1 1 आ गया which is this index. इसमें दोबारा 1 ऐड करेंगे 1 0 1 5 आ गया, इसमें ऐड करेंगे 1 1 1 0 1 1 3 आ गया, और इसी तरह से दोबारा 1 ऐड करेंगे तो 7 आ गया. So you generate these indices. These are called bit reverse indexing. This is pretty much, you know, everything about DFT. Okay, you keep splitting so that you have only 2 points. You can generate indices as well by having bit reverse addressing, and then adding and subtracting, you get these 2 points DFTs, and then these 2 points DFTs are merged to make 4 point DFTs, 4 point DFTs. अगर आप देखेंगे एक स्ट्रक्चर बनता है जिसको कॉल्ड अ बटरफ्लाई स्ट्रक्चर. How many butterflies are there? 4. How many butterflies are there? Again 4. How many butterflies are there? Again 4. So there are n/2 butterflies. And how many stages? Power of 2. So 8 is 2 raised to the power 3. So 3 stages. So n/2 butterflies and n log base 2 n are the number of stages. So these are the number of butterflies in your architecture. So तो ये है जो कि n/2 log base 2 n नंबर ऑफ बटरफ्लाइज आ जाती हैं इसमें, और मल्टीप्लिकेशन कितनी हो जाती है n स्क्वायर से n log base 2 n मल्टीप्लिकेशन हो जाती हैं, बिकॉज एवरी बटरफ्लाई हैज 2 मल्टीप्लिकेशन, सो यू हैव दीज मेनी मल्टीप्लिकेशंस. अच्छा, उससे फ़ायदा क्या हुआ? अदरवाइज एक 1000 पॉइंट का DFT would have taken 10 raised to the power 6 multiplications, whereas the FFT would only take 10 raised to the power 4. 100 orders of magnitude difference. यानी कि एक जगह आप 100 DFT कंप्यूट करें और एक जगह एक करें, सेम वक्त में होंगे. So this is an amazing algorithm, and this is the last topic. और ये बड़ा अहम है क्योंकि जब 4G and 5G की कम्युनिकेशन है वो सारी DFT के तरीके से होती है, ठीक है. It is actually this formula j plus j 2 pi k n over n 1 over n k goes from 0 से n minus 1, which is used to generate the modern day digital communication signal. ये information होती है, ये हर एक को अपने अपने carrier से multiply करते हैं. This is called the multi-carrier, and then you add them together and send. So at the receiver, all you have to do is take FFT and you will get your signal back. So ये बड़ी एक amazing technique है जो कि हमारे digital communication, modern day digital communication uses this. So it has all your cameras, your machine learning algorithms, your radars, they all use fast Fourier transform. So with this, I conclude, and this is our last lecture. शायद ये मेरा लास्ट लेक्चर हो EME में भी, बट वी विल सी. थैंक यू वेरी मच. अगर किसी का कोई क्वेश्चन है तो वो पूछ सकता है. सॉरी मैंने ताकि थोड़ा सा तेज़ चला. You can view it again and again. If there is any confusion, you can always ask questions. लेकिन अगर किसी का कोई क्वेश्चन है तो मुझसे आप पूछ सकते हैं.
सर ये में आपका लास्ट लेक्चर कोई नहीं है, आपकी इतनी आसानी से हमने जान नहीं छोड़नी. So thank you very much. थैंक यू वेरी मच। स्टूडेंट्स, आप लोगों में से किसी का कोई क्वेश्चन है तो प्लीज़ गो हेड, अदरवाइज आई नो सर, मतलब
ठीक है इंशाल्लाह, चलेंगे। ओके,
सर
थैंक यू,
थैंक यू वेरी मच सर, बहुत शुक्रिया सर।
खुदा हाफिज़।